All right, so this is 17.8 divergence theorem. The good news is we basically already know the divergence theorem because we covered Green's theorem, flux version, and that's actually the divergence theorem. In fact, in a lot of books, you'll see it be called the divergence theorem, and in a lot of books, they'll just say Green's theorem, and they mean only the circulation version. All right, so this is actually equal to divergence theorem, planar version. Okay, so this section 17.8 is actually going to be the divergence theorem, the spatial version, the version for triple integrals for solid regions. Okay, so let's actually write down what we already know. So the divergence theorem in the plane is, well, the setting is you have a region R like this, and you have its boundary, which is, well, if you have a two-dimensional region in the plane, its boundary is a curve. All right. So if you have a vector field over this region, then a double integral of the divergence of this vector field over the region, dA, right? Because this is just a regular two-variable integral, nothing fancy, not even a surface integral like we've been talking about recently, just a regular dA integral. All right. Notice this all makes sense. The divergence of f is a function, right? Okay. So this is equal to single integral on the boundary. So this is, again, the stereotypical fundamental theorem of calculus. You have the derivative of something on this left-hand side. You're integrating over a region on the left-hand side or over something on the left-hand side. On the right-hand side, you're looking at not the region, but its boundary, right? In this case, C, which is a curve. And on the right-hand side, instead of having the derivative of that thing, the derivative has disappeared on the right-hand side. Okay, so here it's going to be, it was f dot n ds, right? And the right-hand side, again, is a one variable line integral, right, ds. Okay. All right, this n right here is the outward normal. All right, and that's the only kind of bit of orientation that we have to kind of establish for this divergence theorem. Okay, so this was, again, the divergence theorem in the plane, or I guess in our book, Green's theorem, the flux version. So I wanted to write this down because the one we're going to talk about right now is exactly the same. So we have a solid D, so now 3D. All right, the spatial version. So we have a solid in space. So this is like impossible to draw. So I'm going to put kind of a mini example here. X squared plus y squared plus z squared equal less than or equal to 25. All right. So this is a solid because of the less than or equal to sign. That's the important kind of feature that makes this actually a solid as opposed to a surface. Okay. So this is my D. All right. In this situation, it has a boundary, S. So S is the boundary. Okay, and in terms of our mini example, that would be x squared plus y squared. So the boundary of the solid ball is a sphere. Okay, so what's going to happen is on the left-hand side of my integral, I'm going to be working on D, and on the right-hand side of my integral, I'm going to be working on the boundary of D, in other words, S. All right. Okay, so the left-hand side right here, triple integral. We have a vector field on D, right? Take the divergence of it, dv, right? Just a regular integral, three variable integral from chapter 16. And then here we are integrating over d, all right? And on the right-hand side, you could probably guess what it should be. It's going to be f dot n, all right? So again, we're looking at the outward flux, right? Yeah, I guess I should say, this is the outward normal. Right, and again, this right-hand side represents, so the right-hand side, sorry, the right-hand side up here with Green's theorem represent the outward flux, how much stuff is flowing out of your region. All right. So here in the 3D version, exactly the same. Okay. How much stuff is flowing out of your region and across the boundary, right? And now the boundary is a surface, so we're integrating over S. And then this is d capital S. This is a surface integral. Right? Which makes sense because, again, in our mini example, our S was the surface of the sphere, right? X squared plus y squared plus z squared equals 25. So for example, if we were to do this calculation on this mini example here, right? On the left-hand side, we would be calculating a triple integral of the region inside a ball of radius 25. So perhaps you would, or one option is to transform that into a spherical coordinate integral, where rho equals 0 to 5, and then phi goes from 0 to pi, and then theta goes from 0 to 2 pi, right? On the right-hand side, you would be integrating on the sphere, right? It'd be a surface integral from this chapter, and perhaps you would parameterize that using polar coordinates, where you have rho and, where phi and theta be your kind of u and v, right? Your coordinates, and your rho would be equal to 5. Okay. All right. So oftentimes you can imagine oftentimes in calculation of this particular version of the divergence theorem, the left-hand side possibly could be easier than the right-hand side, because the right-hand side is a surface integral, which we're perhaps not as comfortable with at the moment. Okay. In terms of why this is true, you can prove it exactly like how we proved Green's theorem through the extra credit problem from I guess is 2 weeks ago, where you had to calculate essentially the Green's theorem flux version on rectangles, right? And then what we did the next week was we put those rectangles, we kind of stacked those rectangles so that they created our region, right? Kind of like this. And then the stacking worked out because everything on the boundaries canceled out. Or not, let me say it a little more carefully, everything on the inner boundaries canceled out, leaving only the outer boundary regions which didn't cancel out, which leads to essentially the right-hand side of Green's theorem flux version. Okay, so here, for the spatial version of Green's theorem, or of the divergence theorem, you can prove it exactly the same way. You prove it on rectangular boxes instead of a rectangle, but the proof is almost exactly the same. You have a triple integral, which means you have to use the fundamental theorem of calculus 3 times instead of 2, like you did in the extra credit problem. And then in terms of the kind of more general version, if you're given any solid, you can always break that up into a grid of rectangular boxes, right? And as you let that grid of rectangular boxes, the size of those boxes go to 0, in the limit, you would get exactly this theorem, all right? And again, what's happening is that when you have two boxes side by side, right, adjacent to each other, then the boundary terms on their kind of common side cancel out. And so what's left is only the boundary terms which are not interior boundary terms. And so what you end up with is a surface integral, which is what the right-hand side is right here. All right. In spirit, or kind of intuitively, this is also true because we already know by now that the interpretation of the divergence should be that, well, given any point, if the divergence is positive at that point, it means there's flow coming out of the point, right? It's a source. So the stereotypical picture is something like this, right? Again, the picture does not literally have to be like this, but this is like the stereotypical picture that we always keep in our head. So what does that mean for a point nearby, right? So a point nearby, right? If this one is coming out, then at this point, this arrow has to be pointing inwards. Okay, so when you calculate in a way, again, this is very, very intuitive and not careful mathematics. When you're calculating the divergence of this original point on the left, you're kind of adding up this arrow plus that 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 arrow, right? And this last arrow that I circled is counted as a positive number as it's coming out of the point. But for the second point nearby, right, maybe the arrows look like this, right? When you calculate the divergence there, you're calculating here's out, 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 but that one is in, okay? So what happens is when you have two adjacent points, one of the points, when it's calculating the divergence, it's thinking of this guy as out. The other point is thinking of it as in. So when you add up the divergences at these 2 points, they're canceling out, okay? So this is just a kind of like an infinitesimal, intuitive way to say exactly what we said with these rectangular boxes, all right? But I think this is a good way to think of it because it kind of reinforces the idea that the divergence is an infinitesimal version of the flux, right? It's how much stuff is flowing in or out of a point as opposed to how much stuff is flowing in or out or across a surface, all right? Okay, and again, we're adding up the divergence at these 2 points because that's what the integral is, right? Integral essentially, intuitively means add things up, right? So you're adding up the divergence here, then you're adding up the divergence here, you're adding up the divergence here, and so on, right? And so what you can see is that if I had this idea, right, this arrow, like we said, this common arrow kind of in a way cancels out because it's in for one point, out for the other point. This common arrow cancels out because it's in for one point, out for the other point. And so which ones are not going to cancel out? Well, it's going to be the boundaries that don't cancel out because for example, this arrow here is out for that point, but it's not an in because it's kind of at the boundary, all right? Okay, again, this is, I want to emphasize this very, very heavily. This is not a mathematical proof. This is purely intuition, all right? Okay, and so when you add up the infinitesimal divergences, the infinitesimal flux across out of a point or into a point, when you add them all up, what you get is, well, what the divergence theorem says is you get the overall flux across the region, across the boundary of your region, period. All right. Okay. So on your homework, you're going to find a lot of problems which give you a vector field, gives you a region D, asks you to calculate the divergence. The left-hand side of this divergence theorem, and then they'll ask you to calculate the right-hand side of the divergence theorem, and then they'll ask you to confirm that both are equal. All right. So nothing too exciting, but those are always good problems to make sure you kind of understand that, or to kind of let you literally see that these two things are equal for specific examples. Okay. All right. Okay, so those are some basic problems, but there'll be other problems where you have to kind of decide whether or not to use the divergence theorem. So a stereotypical example is they might want you to calculate the, you have a tetrahedron, something like this, and let's call the boundary of it S. They want you to calculate the flux across the this surface, this tetrahedron, the surface of this tetrahedron. So they want you to calculate this, all right? And potentially this could be a huge pain because how many integrals do you have to compute to actually calculate this? You'd have to break it up to do the surface integral. You'd have to break it up into 4 panels, right? You've got this bottom panel here. You've got this panel on the left there. You've got this panel on the right there. And then you've got the panel that's facing us, right? So this involves 4 integrals. 4 surface integrals. Let me emphasize that. Right? DS integrals. And anytime you do a DS integral, you have to do a parameterization, right? You have to calculate the Jacobian and so on. So a bit of a pain, right? So if you're asked to do this, an alternative option is to calculate So possibly can calculate the triple integral over the inside of the tetrahedron, right? Over the interior of the tetrahedron, d divergence f dv instead. All right. So in this case, it would just be a triple integral, right? Which hopefully we're in a way more comfortable with, right? And depending on the structure of this tetrahedron, it could be it could very well be that you have fewer integrals to do. It might even be just one integral if let's say this tetrahedron was kind of like a right tetrahedron, where it's the three panels in the back are made up of vertical planes, right? So so there's x, y, and z. So the xz plane, the yz plane, and xy plane. If those are three of the panels, then you're actually only going to need to do one integral, right? Volume integral, where you integrate dz first from 0 down to this front plane, right? And then the shadow of your region would be this triangular region down here. So in this case, you would only need to do one integral, one triple integral, as opposed to four surface integrals. All right. Of course, if it wasn't as simple, if this tetrahedron were kind of tilted so that it's more like maybe like a pyramid, right, where this center point comes down in the middle of your triangular region, then you're going to have to break it up into, or you're going to potentially have to break it up into multiple integrals. All right. But this is always an option for you. Of course, I say possibly because, well, ultimately it all depends on what goes in here, right? Maybe this is only one integral down here, but if the divergence of f happens to be really nasty, then maybe you're not able to actually compute that integral, right? Then maybe you have no choice but to do four separate surface integrals. All right. So all of these kind of, I guess last time we talked about tips and tricks for Stokes' theorem. All those were based on possibilities. Ultimately, again, you're going to have to integrate some function inside here, and if that function doesn't cooperate with your region, you're just going to have to perhaps go with the other option, which may not seem as nice, right? Four integrals versus possibly just one. There might be nothing you can do about that, right? But at least you have the option. And oftentimes you'll see exercises in the book where one of the option that they present to you immediately is actually really difficult or actually a huge pain, whereas the other option actually does turn out pretty nice. Okay. All right, so this is a very stereotypical example. If I remember correctly, I think there is a problem that's almost exactly like this on the online homework. All right. On the other hand, of course, if you're asked to calculate, right, integral divergence of f dv, right, the kind of sum total of the divergences of your vector field inside a region, well, you always have the option instead of calculating f dot n ds. All right. Okay. Oh, by the way, I also want to say up here. Let me just say down here actually. So my first kind of example here was, maybe you want to use the divergence theorem when you're given a surface integral. Maybe you want to do this divergence integral down here instead, because the regions, make it so that might be easier. But an alternative reason that might be easier is, for example, maybe you recognize the divergence is simple, right? So this is very common where you're working with a vector field that's divergence free. So if it happens to be divergence free, of course, then immediately that this triple integral down here is going to be 0, right? Divergence f is equal to 0. And so that automatically means that this surface integral up here is also 0. Right, so then you could get it without barely any calculations. You just have to, maybe quickly check, is the divergence of f something really, really nice and simple? Okay, so that's an alternative reason you might want to go from the surface integral to the triple integral. Okay. All right. By the way, so this tetrahedron example shows us that oftentimes the surface integral is quite complex, but if we did look at our first mini example where we were working with the sphere, then both integrals, or the solid ball, then both integrals would just be a single integral, right? However, if you have something like your region is the inside of a paraboloid, let me actually write a kind of careful region here. So let's say x squared plus y squared bigger than or equal to z squared. Sorry, less than or equal to z squared, right? So this would be the stuff inside the paraboloid, right? And let's say z less than or equal to 4, okay? Then there would be a cap, right? So your region would be everything inside this kind of cup here, right? Your boundary would be x squared plus y squared equals, sorry, not equals z squared, less than z. I want a simple paraboloid, sorry about that. Equals z, right? That would be the paraboloid, right? So just this part. And then plus z equals 4. Okay, so these would be your two integrals. So this would be the cap, okay? And of course, which part of the plane z equals 4? Only the part of the plane where x squared plus y squared is less than or equal to 4, right? And then which part of the paraboloid? The part of the paraboloid where z is less than or equal to 4, okay? All right, and again, always be aware of the outward normal, right? So the outward normal, for this one, your normals would be pointing like this, okay? So it's outwards in this picture, or in this description, but remember that alternatively, in this particular example, it also means downwards pointing, right? Because each of these arrows have a negative k component, all right? So be very careful about that. And for this cap, outward normal would be upwards pointing, okay? And also for the like the tetrahedron example, you better make sure if you're going to do it with the surface integral, do it as 4 surface integrals, then you need to make sure you've got the normals correct, right? Or else you're going to be adding them up wrong. So for example, this normal would have to be pointing that way. This normal would have to be pointing that way. This normal would have to be pointing downwards, right? And then this normal would have to be pointing outwards like this, okay? And then, depending on the surface, you're going to have to kind of figure out how to determine whether your normal is outward pointing. All right. So, for example, in this tetrahedron, this side face right there, that's on the xz plane, right? The normal that you want would be the one that's pointing in the negative y direction. Okay. So actually, it would be literally negative j, right? This one right here on this side panel, the xz plane panel, the outward normal would have to be negative I. And then as you can see, this one over here, the bottom panel, the outward normal would be negative k. All right. Whereas this final panel, the one that's facing us, not necessarily so easy to determine, but thinking about this picture, right, this is the panel that's kind of facing us. And so this normal here has a positive z component, all right? So when you calculate, make sure your normal has a positive z component, okay? All right, so that's one thing to be very careful about, especially when you're working with multiple surfaces. It's really easy to get one of the surfaces, do the wrong normal for one of those surfaces, and then, of course, when you're adding them up, you're not going to actually get the right answer. Okay, so maybe a more complicated example or more complex example. So let's say, let's actually use this something similar to this paraboloid up here. So let's say we want flux across paraboloid. Z equals x squared plus y squared, and let's say z less than or equal to 4. So same kind of idea as our discussion up here. But now we just want the flux, let me say, of some vector field. Okay. And oriented. So here we're going to have to give an orientation because the problem is just that we want the flux across the surface of the paraboloid. This is not a closed surface, right? Because this is just this part of the paraboloid without the cap, all right? So here we're going to actually have to explicitly say what orientation, right? Do we want the normal to be pointing here, or do we want the normal to be pointing in the opposite direction? Okay, so again, this one would be downwards, perhaps, right? Or a good description of it would be downwards. And this one would be upwards. Okay. So let me say oriented with n equals upwards. So let me just put that in quotes. So let's say we want this, right? So again, what we're trying to calculate is how much fluid is moving across this surface, right? From, in a way that, from this side of the paraboloid to the other side of the paraboloid. Okay, I'm trying to be a little careful not to say inside and outside, because there is no inside and outside if we don't close this up. Okay, so this problem as it's stated is merely just this guy here, right? S, let me call this guy S, right? F dot n d capital S. So it's just one surface integral, all right? Now, one situation where you might want to use divergence theorem is maybe this integral is just too hard, right? Maybe f dot n ds is too hard to actually integrate, right? Once you parameterize and all that, you realize f dot n ds is too hard to integrate. Or alternatively, for maybe a more complicated problem, maybe the surface is too hard to parameterize. You don't know how to parameterize it, right? Maybe if it wasn't as nice as a paraboloid, I gave you something that looked wiggly like this, right? Then perhaps you don't even know how to parameterize it, right? So an option is to close up the surface by creating a region and creating the kind of other part of the boundary, right? So here again, we only have a paraboloid. What we do is we can kind of close it up like that, right? So here we have our original S, and then now I've made up a new surface S1, okay? Now this guy here encloses a region, right? So now I can say the region D. Now this phrase makes sense, the region D, right? The boundary of D is S and S1, right? So triple integral D divergence F dV is equal to double integral S F dot N ds. This is the guy that we actually want, plus double integral S1 F dot N ds, right? So we want this, but it's too hard to calculate. So what we can do alternatively is instead we calculate this guy here, and we calculate this guy here. We subtract this guy here to the other side, and we've got the answer for the guy that we want. All right? So again, the hope is that this is easy, right? We hope this is easy, and we hope this is easy. And then once we've calculated again, we can just throw this guy on the right-hand side to the left-hand side, and we've got our answer, all right, subtracting it. Okay, so the important thing here is that we had to fabricate this S1, and we had to fabricate this D, right? So as stated, the problem doesn't have an S1, it doesn't have a D, all right? So it's very much like, I think we had problems in the Green's theorem flux version section that were like this as well. So this is pretty much the same analogous type of problem, except of course now we're working with regions in space or solids and surfaces as opposed to regions in the plane, right? And curves. All right. So one advantage here is that or one thing that can often help is that, for example, like in this problem, if we close it off like this with just a flat panel, right, the integral of this S1 right here is going to be relatively straightforward, right? The parameterization is going to be super simple. The setup of the double integral is going to be relatively simple. All right. So so hopefully, this is something that might work. However, notice one thing here. You don't necessarily have to cap it off kind of in this obvious manner, right? So I capped it off with just a flat plane like this, and then this was the inside of that was my region. But potentially I could cap it off like this, right? And then S1 would be this, S2 would be this. My region, my D, would be now the inside of this bubble, the whole bubble, right? And the calculation of S1 would be kind of like a bubble integral on this upper bubble, right? Now, why might you need to do that? It could be that this flat integral here is too hard. So, you have nothing else you can try but maybe other surfaces, okay? All right, but usually, for introductory classes like this, things work out pretty nicely with kind of the obvious, in a way, version of closing up the region. Okay, so the kind of final thing here is what happens if we have a region with holes in it. So for example, what if D is equal to x squared plus y squared plus z squared, I should have left some space here, between 25 and 4, right? So this would be the region inside a sphere of radius 5, but outside a sphere of radius 2. All right, so it's a sphere with a hole in it. All right. So how does the divergence theorem work here? Well, it's exactly the same. So divergence, but you do have to be a little careful. Divergence f dv over our region D, right? This is going to be double integral over the outside sphere. So let me write it like this: x squared plus y squared plus z squared equals 25. All right, f dot n ds plus integral x squared plus y squared plus z squared equals 4 f dot n ds. All right, because the boundary of this D is comprised of the outside sphere and the inside sphere. Okay. However, we do have to be careful. This normal here points. So the normal should always be the outward pointing normal, right? So this normal here, outward pointing, is our usual concept of outward pointing. All right. So let me be a little more precise by saying points away from origin. All right. Okay. But outward pointing for this guy down here, for x squared plus y squared equals 4, is actually going to be the one that points like that. So this one is going to point inward, towards the origin. Okay, why? Because when we say outward pointing normal, outward normal, we mean outward relative to a surface. It points away from the surface, or away from our region. Okay, so this is directly analogous to the situation where in the plane, this is your region, right? So then you would have two boundaries, the big circle and the smaller circle. For the outside big circle, your normals point like this. Again, at this point right there, you're pointing away from your region. The other normal is pointing like that, which is into the region. Okay, but for the smaller circle here, the outward normal is pointing like that because the other normal points into the region. All right, so outward is always outward relative to your region. Okay, so when you do this calculation here, this normal right here has to actually point towards the origin. Okay, so be careful about that. This is actually a very important case. So it might seem that this is just some made up example to make students suffer. But But these cases are actually really important because oftentimes, I think we said this when we did this example with Green's theorem as well. In situations where your vector field is not defined at a point, right? And we've seen many examples of that, especially for rotational vector fields. If your f is not defined here, let me do it down here. If your f is not defined here, then if you still want to kind of use the divergence theorem, then what you do is you take a tiny circle here and a big circle like that, and you can now you're allowed to do the divergence theorem because now the vector field exists everywhere here, right? The problem point where f does not exist is not in our region. Okay, and so you can apply the divergence theorem like this, and then you can get a lot of important information like this from the divergence theorem. In fact, one of the online homework problems actually discusses this, and it's a really, really important example in differential equations, because one way to solve partial differential equations in general is to use exactly this technique. And in fact, what pops out of this for the two-dimensional case is what's called the Green's identity, named after Green's theorem, all right, or named after the same dude. So this is not a contrived example. It's actually a really important class of examples that that we use to actually study real things, because in real life vector fields might not be defined, and so you're going to have to kind of cut out a hole of your region when you actually apply your theorems. Because of course, right, none of these theorems are legal if the thing that you're trying to integrate is not legal, right? You can't integrate divergence f over a region, over the entire region here, if f isn't defined at that point, right? That's completely illegal. So you're going to have to kind of create holes like this, and then kind of take limits and things like that to kind of work things out. Okay, so this is the three-dimensional version of the divergence theorem. As you can imagine, you can easily extend this to 4 dimensions, 5 dimensions, 6 dimensions. Everything we talked about is perfectly legal and perfectly makes perfect sense, right? In 4 dimensions, you do a 4-dimensional integral here, divergence of f, right? D whatever, I'm still going to call it dv. It makes sense, right? The divergence of f, if you have f depends on 4 variables, depends on 4 entries, right? So we're in 4 dimensions here. If we have, let me say it like this, x, y, z, w, right? Then the divergence of f would be df dx plus df dy. If it's pqr, let's say pq, dr dz, and then d whatever dw, right? D or s t. Let's use u, right? Where f is equal to p q r u. Okay. So perfectly legit, right? And again, the divergence is exactly what you would expect. You just add this term here, the derivative of the 4th entry with respect to the 4th variable. And the right-hand side would be exactly as you would expect. It'd be a triple integral on the boundary of D, right? But now the boundary of D would be a solid, okay, a 3-dimensional thing. So this is a triple integral, and f dot nds, or d dv, right? This is a triple integral v. That is a quadruple integral v. But here, this makes sense because in a 4-dimensional setting, right, a region, you still have on the boundary the concept of inside and outside. Okay, so everything still makes sense. So this can be extended into any number of dimensions and is true for any number of dimensions. I just wanted to mention that because notice we haven't talked about a Stokes theorem for 3 dimensions or any higher dimensions, because, well, the way we kind of talk about Stokes theorem, it doesn't make sense in terms of circulation, because Stokes theorem, you have double integral s curl f dot n ds equals single integral on the boundary f dot t ds. right? If you wanted to do a triple integral version, first of all, how would you, the curl is a vector field, right? So there is no dot n. There's no concept of dot n, right? With a surface, there's a concept of dot n, which is the normal to a surface in space, right? So you already have problems right there. And then on the right-hand side, this is supposed to be the circulation around the boundary. So as you move along the boundary, how much how much liquid or whatever is flowing around, right? That doesn't really make sense if you're doing this guy here down here, because this right-hand side should be a surface integral. And what does it mean to have circulation around the surface, right? Doesn't really make sense, right? Whereas again, you can have circulation as you move around here because it's just a curve. So there is no extension, at least we're not certainly talking about any extension of Stokes' theorem for higher dimensions. Notice also we have a version of Stokes' theorem for surfaces and their boundary curves, but we have no version of the divergence theorem for surfaces and their boundary curves. All right, because it doesn't quite work that way. You have to redefine the divergence, and that's way too much for our class. So our version of divergence works because we're in space or in the plane, and space and plane are flat. But once you're on a surface, our kind of naive concept of divergence, which is dp dx plus dq dy plus and so on, would has to be modified to have it mean what it's supposed to mean. All right. So we're only working in a very, very simple setting, so that we only have kind of the basic divergence theorem. Okay. So that's pretty much it for what we actually for our class. This was the last section, but this last chapter we've talked about a whole bunch of different theorems. We've talked about the divergence, the curl. We've talked about the gradient for the entire class, and all our theorems seem very similar, right? They're all kind of fundamental theorems of calculus, but they all are in a way different, right? One of them has a curl, one of them has a divergence. How do all these things relate to each other, right? So let me give a very quick discussion of this. So the idea is we have functions, all right? So functions are functions. First of all, let me set this up. We're in space, all right? So what do we have? We have functions, all right? So nothing exciting there. The functions are functions. We have, so let me give this a title. Gradient, divergence, and a curl. So I'm gonna try to tie these three guys together, at least kind of, give you an idea of how all these things are related to each other. So this only works in space, and we'll kind of see why actually. And also in this discussion, we'll kind of see why the curl is something that only lives in space. Okay, so f of x, y, z is a function. So actually there's this mathematical construct that we could do called df, all right? And for our purposes, it's essentially like the gradient, all right? So what happens is, we kind of talked about this when we talked about linear approximation. I always like to use the deltas, right? In linear approximation, delta x, delta y. And I think I'm pretty sure I said I didn't like the notation dx and dy because those guys were reserved for other mathematical purposes. And the other mathematical purposes is what we're talking about right now. So what we have is functions are what we call zero forms. All right. We move up, we can have one forms. And essentially, those are like vectors or vector fields. All right. So df would be something where if you give me a function, the output of df, or the df is equal to df dx dx plus df dy dy plus df dz dz. All right, where dx, dy, and dz are kind of the basic one forms. Okay, more technically, they're actually things that are operators. They're something that if you give me a vector, then this thing applied to it gives you a number. All right, but we don't have to know that kind of amount of detail for this discussion. But just let it be known in a way that these guys actually have very mathematical meanings. All right. Okay, so one forms are essentially the gradient, right? Because the gradient is df times I. F sub x, f sub x I, right? So here the dx is kind of like the I. Df dy times j, right? Which is like the dy. And then df dz times the k. Okay, so one forms are essentially like vector fields. So let me kind of do this. They're like vector fields. Okay, now let's get something more interesting. There's such thing as two forms, and what they are things which are combinations of the dx's and the dy's and the dz's. All right. So, for example, dx, the notation we use is dx wedge dy, dy wedge dx. So all the possible double combinations. All right. So dy wedge dz, dz wedge dy, dx wedge dz, dz wedge dx. All right. And technically, mathematically, these guys are, again, operators. What they do is they take an input of a vector, comma a vector, and give you a number. Okay. So again, these guys have technical mathematical definitions, but we don't really need to know it for this discussion. The important thing for our discussion is that are two things. One is that this wedge thing is antisymmetric. So if I swap the order, so if I go from dx wedge dy, how does that relate to dy dx, dy wedge dx? These are negatives of each other. All right. So this is equal to, this guy is equal to negative of this guy. All right. So that's usually what we call antisymmetric. So dy wedge dz is negative of dz wedge dy. All right. So this is negative of that. All right. And dx dz is negative of dz dx. So there's this antisymmetry going on. All right. So in fact, there's only two forms: dx wedge dy, dy wedge dz, and dz wedge dx. Right? The other three are actually just order swapping of these three guys. Okay? Are negatives of these three guys. Okay. So two forms, we can do with two forms what we do with one forms, right? With the one form here, we have something times dx, or something plus something times dy plus something times dz. So two forms, you can do combinations as well. So you can have f, or let me not use f, so let's say p dx wedge dy plus q dy wedge dz plus r dz wedge dx. All right, where these guys are three variable functions. Okay. Now, how do one forms and two forms relate to each other? Well, if you have a one form, let's say f d, let me use p, q, and r again. P dx plus, I shouldn't have used p, q, r there. Let me do little f, little g, little h here, because I want to do this next example with p, q, and r. P, q, d, y plus r dz. You can do something called d of this. All right. And what we did up here when we talked about d of a function is we took the derivative with respect to x, right? And then dx. The derivative with respect to y, dy. Derivative with respect to z, dz. So that was d of a one form. So d of a two form, that was d of a function, right? D of a zero form gives you a one form. D of a one form gives you a two form. All right, so d of a one form gives you a two form, and the kind of formula here is this is dp dy. Well, let me give a kind of first technical definition. So this is dp dx dx wedge dx plus dp dy dy wedge dx plus dp dz dz wedge dx. All right, and then you can imagine, you can kind of guess the rest of them. It's going to be dq dx dx wedge dy, right, plus dq dy dy wedge dy plus dr dy, sorry, dq dz, getting ahead of myself here, dq dz, dz wedge dy, right? So it's always dq dx wedge dy, right? Because q is q dy, right? So this is dy dy wedge dy, dz dz, and then dy. And then finally dr dx dx wedge dz, right? Because this one, r is based on dz's. So dr dy dy dz dr dz dz dz. Okay. Okay, looks terrible, but remember this anti-symmetry. If you swap the order, you should pop out a minus sign. But if you swap the order of dx dx, you get the same thing. But you still need to pop out a minus sign, which means dx wedge dx is equal to negative of dx wedge dx. How can something be the negative of itself? It has to be 0, right? So this is actually 0, 0, and 0. Okay. All right. So ultimately, we can combine a lot of these other ones too, because you've got dx dy wedge dy. That can be combined with dy wedge dx, right? Because dy wedge dx is negative of dx wedge dy, right? And we can do that for, let's see, so let me underline these. We can do it for these two. We can do it for dz wedge dx is the same as dx wedge dz, right? And finally, we have dy dz wedge dz is the same as dz wedge dy, right? And so this is ultimately equal to dq dx minus dp dy dx wedge dy, right? So this minus sign comes from swapping the dy and the dx. Let me write like this, minus, where is this? The blue ones. So, oh, sorry, yeah. All right, let's write this as dr dx. Minus dp dz, right? So this would be the blue ones. And then there's a minus sign here. So I'm going to write this as, this should be dz wedge dx. And then finally we have dr dy minus dq dz. All right, so these two green ones. Dy dz. Okay, so why did I go through this horribleness? Well, this is the curl. This term here, right? So let me show you the curl, right? If I take the curl of PQR, IJK, ddx, ddy, ddz, PQR, right? This is curl of F, right? Again, F is equal to PQR. Okay, so if I had a vector field given by PQR, the curl is going to be what? This is going to be I times dy dr dq dz. Let me just write it kind of quickly. R sub y minus q sub z, right? Minus j times r sub x minus p sub z, and then plus k times q sub x minus p sub y. All right. Okay, so what you'll see is this first guy up here, the dx wedge dy, corresponds with this k term. Exactly. dq dx minus dp dy. qx, py. All right. The middle one, dr dx minus dp dz, right there. all right? And the last one, dr dy minus dq dz, ry qz, okay? So essentially, this idea of d of a one form, it's like a curl, right? And it looks kind of strange how we did the correspondence, but the idea is this one, sorry, this one here is missing the dz, right? And so that corresponds with the k. The guy that it's missing with, the term that it's missing of the three is the one that it corresponds to down here. This one is missing a y, so it corresponds to the j. All right, and this one is missing the z, the x, so it corresponds with the I. All right, and so if you look at this, right, dy, dq, that corresponds exactly with this. So that's actually a correspondence between the d of a one form. So d of a one form is essentially the curl. Okay. All right. So things are actually a little bit more, make a little bit more sense here, hopefully now, because we also have d of a zero form. That's equal to gradient, right? We've already said that, right? D of a function is essentially like the gradient. All right. Okay. And notice that this only works in 3D, right? Because in 3 dimensions, we have dx, dy's, and dz's. So if you take a vector field, right, and you take d of it, as we did here, kind of, then you're going to end up with a 2 form. But because a 2 form is missing one thing, you can translate that back into a vector field, right? So there's this idea called a duality, right? So what we have is we have 0 form, 1 form. So I'll write a stereotypical one, dx. We have 2 form, dx, dy. And then we can also talk about 3 forms, dx, wedge, dy, wedge, dz. But for now, we'll talk about that in 1 sec. When we take d of something here, we get something there, right? But things here corresponds to things there, right? dx, wedge, dy, in a way, corresponds with dz because it's the one that's missing. All right, so anything that lives here, we can translate it to something here. And anything that's here, we can translate it to something there. All right, so there's this natural transformation between these two guys. All right, so let me actually write it here. So dx wedge dy corresponds to dz here. Okay, actually, let me write that here just to make it not look confusing. All right. Okay, so what happens is when we have a vector field f equals pqr, right, we can think of that as something that lives here, right? It's p dx plus q dy plus r dz. Okay, so we can think of a vector field as something that lives here. We can take d of it, then it becomes something that lives here. All right, but things that live here, we can retranslate back, right? We can reinterpret it as something that lives in the dz realm, right? And if we do that, we get a curl. Okay, so this kind of translation backwards is what we usually call a star. It's a star mapping. It's a star correspondence. All right. So essentially, what we're doing is we're saying if I have a vector field, I can think of it as d of something. All right. So let me say if I have a vector field f, I'm going to call this something omega. All right. So omega corresponds to f. This is a vector field. This is a 1 form. Okay. So what happens is if I take d omega, now that lives here, but I can take this star kind of correspondence to push it down to a 1 form. All right. So star of d omega, that's actually a 1 form. All right. So let me write it out carefully. D of omega is a 2 form. Right? But 2 forms are essentially 1 forms. So star of d omega is a 1 form, which we can make a correspondence with. That's a vector field. And that vector field is the curl. All right, that's what we call the curl. all right? But in reality, this over here, star of d omega, is kind of the right way to think of it, all right? Now notice this, like I said, this only works in 3 dimensions because this correspondence, the way we kind of described it was, there's only one guy missing from dx wedge dy, there's one guy missing, dz, right? So whatever your coefficient of dx wedge dy is, that goes with dz, right? So if you were, let's say, sine of blah, 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 dx wedge dy, now when you do this star correspondence, now you're sine of blah, 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 dz, okay? But if we were in 4 dimensions, then dx wedge dy would be missing 2 things. It would be missing dw and dz. So you can't make this correspondence anymore. So 2 forms would not have a correspondence with 1 forms in 4 dimensions. All right. So this correspondence only works in 3 dimensions. And so that's why the curl only exists in 3 dimensions. All right. Okay. Now, what are 3 forms? 3 forms, there's only one 3 form because everything else, right, all other combinations like dy, wedge, dx, wedge, dz, right, you can swap the orders of them and pop out minus signs, right? And so here I can swap these 2 guys. So this is equal to minus dx wedge dy wedge dz, right, which is negative of that, okay? So if you think about it, there's only one 3 form. It's dx wedge dy wedge dz. All the other combinations are plus or minus of this guy here, okay? So in a way, there's this correspondence between 3 forms and functions, right? Because a 3 form, a stereotypical 3 form would just be something times dx wedge dy wedge dz, right? And what is that something? That something is a function, right? So what is a function? A function is a 0 form. Okay, so just like there's this correspondence between 1 forms and 2 forms, there's a correspondence between 3 forms and 0 forms. All right, and we call that, the name for that correspondence is, again, star. All right. Okay, now why do I care about that? Well, because, oops, what happened there? Okay, because the divergence, let me redraw this. We have 0 forms, oops. We have 0 forms, we have 1 forms, we have 2 forms, we have 3 forms. Right, typical 0 form is, again, a function. Here is something like dz, here is something like dx wedge dy, here is something like dx wedge dy wedge dz. Okay, so what's the divergence? So divergence is, well, we start with a vector field, which is something that lives here, right? Now, the curl was, we took d of this guy and we got to here, to a 2 form, and then we took star to come back, okay? So let me actually write that again. So if I have omega here, vector field, right? I move it to here via d, and then I can move it back. So this is d omega using star. Okay, so star d omega. All right, it's just like a composition of a function. Now, alternatively, I could do this. I start with a vector field, right? Again, here these guys can be thought of as vector fields. I can move it to here using star first. All right. Okay, so I get something star omega. Okay, so this is actually very simple because p dx plus q dy plus r dz just goes to p dy wedge dz plus q dz wedge dx plus r dx wedge dy. All right. So this guy here is super simple correspondence. But now what I can do is I can take d and move to a 3 form. All right, so d star omega. Okay, what is d of a 2 form? Same idea, right? So if I take a 2 form, for example, p dx wedge dy, right? If I take d of this, I'm going to differentiate p's in all the different possible ways, right? So this is going to be dp dx, dx wedge dx wedge dy, which is 0 because we've got dx wedge dx, plus dp dy, dy wedge dx wedge dy, right? Which is 0 because we've got 2 dy's, all right? Plus dp dz, dz wedge dx wedge dy, all right? And so this ultimately is the same as dp dz, dx wedge dy wedge dz, okay? All right, But what was dx wedge dy? This corresponded to, over here as a one form, this corresponded to p dz. All right, so p dz goes all the way to dp dz. All right, so the coefficient of the z term gets differentiated by z. All right, so that's actually what we do with the divergence, right? But here, the divergence is supposed to end up giving us a function. This is not a function, right? This over here is a three form. But like I said, three forms are the same as functions. So I can do star of this, right? So this, so far, what I have is d star omega. If I take another star of that, I'm going to end up, yeah, let's do it like this. I'm going to end up here. So this is going to be star d star omega. Okay, now this guy here is the divergence. All right, so this one kind of description, this idea of differential forms allows us to talk about the gradient, the curl, and the divergence all unified within the context of differential forms. Okay, so this is why, you know, when we first learn vector calculus, things seem so weird. We have like several different, very different objects, curl, divergence, and all that. But in fact, they're all unified under one kind of theory in a way. All right. Okay, but there's more. Everything is unified under this. Here's a very interesting thing. You could check this out yourself. If you take two d's in a row of anything, a one form, a two form, a zero form of any form, you get zero. All right. So again, you can check this just directly from kind of our concept of what d is. All right. Okay, so who cares about this? Well, let's start with a function. We have a function here. If we take d of it, right, let's take d of it, we get df. That's a vector field, right? How do we take the curl? Well, let's look back up here, right? What was the curl? It was star d omega, right? Star d of this, okay? So if I want to take the curl, I have to take d of this, ddf, and then I have to take star of it. But ddf is 0 already, right? So when I go to here, I'm just going to get 0. All right. So what did I just say? Essentially, I said if I do the gradient first and then I do the curl of a function, I get 0. All right. So this idea that d twice in a row gives you 0 tells us exactly this guy here. One of the identities that perhaps in vector calculus, if you only knew vector calculus, it's something that you just have to memorize, right? Or you'd have to kind of compute it by hand just to confirm it every time. But up here with this description in terms of differential forms, it's all unified in just the fact that two d's in a row gives you 0. Okay. All right, we also had another identity, right? We had divergence of the curl of a vector field. That was equal to 0 as well. But that's explained with the same thing. Two d's in a row gives you 0, right? We just said the curl is you do a d onto your thing. Again, I'm going to call it omega because that's kind of a more conventional name. So f corresponds to omega, right? Of course. Okay. What's the curl? You take d of this and then you take a star. All right. Now, what's the divergence? The divergence we just said was you take star d star. Okay. But what happens if you take two stars in a row? Well, what happens is, for example, if you take star of something here, you go to there, and then you take a star again, you're going to come back to there. And in fact, you just come back to the exact same place. All right. If you take a star here, you're going to go to there. If you take a star again, you're actually going to come back to the exact same place. Okay. So two stars in a row is just identity. So you've done nothing. So this is actually equal to star d dw. What is that? Two d's in a row, that's equal to 0. Right? So this identity that perhaps you had to memorize, or if not memorize, you know, to reproduce it, you'd have to actually calculate the definition of curl from the definition of curl divergence. It's actually unified under just the fact that two d's in a row gives you 0. All right. Okay. And what is divergence of the gradient? Well, that's the Laplacian. That's not 0 because if you think about this, this is df and a star d star, right? There's no two d's in a row because there's a star in between. Okay. And so this is not 0. which again we know is true because it's a Laplacian of f. All right. Okay, so you can play around with these kind of stars and d's for yourself just to see what happens with them, which ones should be 0 and stuff like that. But these are essentially, the main ones. By the way, earlier I said that the divergence, we don't have a divergence theorem in our class for surfaces and boundaries of surfaces, right? Even though we have something like that with Stokes' theorem. And that's because when you extend a divergence theorem to surfaces, it should no longer look like this anymore. All right, so things actually become a little more complicated. The divergence actually has to become a little bit more complicated. Okay, so that explains a lot of this, why we have the curl only in 3 dimensions in particular, right? So you're never going to hear about if you're working in 4 dimensions, 5 dimensions, you're never going to hear about the curl because it's something that's not natural, right? You can't kind of do this correspondence in order to create a curl. Whereas the divergence makes sense, right? Even if you have like 10 dimensions, let's say 5 dimensions, right? If you have a vector field here, right? You can take star of it, you get a vector field here. When you take d of that, you get something here. When you take star of that, you get something back here, right? And that's basically the divergence in the flat plane in R5, right? So that's perfectly legal, right? If we tried to do the same thing with the curl, right, we would have started here. We take d of it, that would be here. When we take star of it, right, we don't end up back at 1. We end up here. All right. So this is not a vector field anymore. So the curl, if you tried to do the same thing, it would not be a vector field. Okay. All right. And again, that's because the star operation, kind of fills in what's missing, right? And so when you do the count, right, the things that are missing is not going to be compatible. So this is our very interesting unifying kind of theory for all of this. Oh, I guess I should say, and you can kind of talk about all our fundamental theorems in a way, let me put big quotes here, as d of something is equal to just integral of that thing. All right. This can be made more very, very precise, but I think we've gone quite long already. But if you do take, for example, a differential topology class, or especially if you become a math major, you take a differentiable manifolds class, this is something that you would talk about. And this framework here, these Ds and these stars, create a framework for, again, we talked about classifying geometric objects, mathematical objects, topological objects, and also provides a framework for studying topological geometric objects, extensions of the idea of a surface or a solid into higher dimensions and so on. All right, so really interesting stuff. If you're a math major, you should certainly try to find a differential topology or a differentiable manifolds class. You'll talk about how loops give you classifications, just like how we talked about loops. The loops give us an understanding of simply connected, which is related to vector fields, which is related to this D stuff, right? All of this stuff ties together really, really well in the future if you're a math major. But unfortunately, when you learn this in vector calculus, it's just a lot of disparate looking theorems and mathematical kind of objects, the curl and the divergence. They seem very, very different. But in fact, they're in a way, not different at all. Okay, so I think we've gotten a little long, so we'll quit here.